In the last video, I asked, when was gas giant theory first discovered? If that prompted you to Google an answer, you would have found it difficult to find a date for the theory's discovery. Really, I should have said, when was the theory first proposed? But never mind, it makes no difference, because gas giant theory doesn't have a date of first proposal. The theory slowly emerged by sliding consensus over the 19th and early 20th centuries. In the 19th century, one of the big questions of natural philosophy was, how did the sun burn, and for how long? Geology played a part in stimulating this question. Stratigraphy had become a popular subject for 19th century geologists. This is the study of layered rock formations. Stratigraphy prompted geologists to attempt to chronologically order rock layers, and this led to an attempt to age all rocks on Earth and the Earth itself. And geologists kept revising their estimate for the age of the Earth upwards. There was some communication between the 19th century astronomy and geology communities, and since it seemed logical that the Sun should be at least as old as the Earth and likely older, the increasing estimate of the age of the Earth prompted astronomers to look for physics that would have kept the Sun burning for at least as long as the Earth was old. Bear in mind, natural philosophy was replacing theology in explaining reality, so theorists had the first task of shifting consensus away from the theological estimate of the age of the Earth, which was around 6,000 years. Astronomers had first looked to chemistry to explain the Sun's energy, but chemistry could only keep the Sun burning at 5,500 degrees for a few thousand years. Gravity was the theory that the 19th century astronomers had specialised in. They calculated that gravitational collapse of stellar masses had potential to release vast amounts of energy. This could heat the Sun sufficiently for about 10 million years, so theorists favoured gravity collapse for a while. But soon consensus from geologists required a far greater time span for the Earth and Sun. By the early 20th century, geologists were suggesting the Earth was hundreds of millions of years old, or even older. It wasn't until nuclear fusion theory in the 1930s that answers that satisfied both geologists and astrophysicists were available. The Sun was large enough to contain a reserve of nuclear fuel to keep it burning for billions of years. The model that 20th century astrophysicists had arrived at was a synthesis of the 19th century gravity collapse model and the 20th century nuclear physics. They theorized that stars were the result of collapsing gas clouds. The gas was heated to millions of degrees by gravity collapse, and this heat ignited nuclear reactions, which then kept the star burning for millions of years. Astrophysicists then explained the creation of Jupiter the same way they explained the creation of stars. They said Jupiter was created by gravity collapsing a mass of dust and gas. But unlike a star, it never got big enough to ignite nuclear reactions, so it cooled into a gas giant planet. That was one reason for the gas giant theory, and it's quite a well-known story. But there is a slightly less well-known story that was equally important in the history of the gas giant theory, and it's this second story that draws my criticism and leads me to believe the gas giant theory is wrong. I'll reserve judgment on that first story for later. In my previous video, I mentioned planet modelers were using the estimated average density of 1.33 grams per cubic centimetre for Jupiter in their models. A value of 1.33 fits the theory that Jupiter is mostly condensed hydrogen, and since this is in line with the gravity collapse theory of the solar system, planet modelers and the astrophysics community as a whole were happy with this density estimate. But where did it come from? Certainly no one has gone inside Jupiter and checked the density of the material there. In the 1680s, Isaac Newton proposed that gravity force between any two bodies was proportional to the product of their masses and inversely proportional to the square of their separation. The success of Newtonian gravity to explain solar system motion and gravity on Earth is well known. What is less well known is that Newton didn't include big G in his gravity formula. Instead, he left open the possibility that gravity was also proportional to other factors. Perhaps properties of the matter involved, perhaps some universal constant. In the 1680s, there was no other known factors that could be reasonably argued to affect gravity. For anyone trying to use Newtonian gravity to model celestial mechanics, this presented a minor frustration. They could now explain gravity laws in terms of forces, but it still wasn't possible to quantify the forces or the masses of the celestial bodies of the solar system. Yet Newton's formula seemed to make quantifying those properties tantalizingly close. Throughout the 18th century, astronomers were still stuck with the same problem. They still could not obtain gravity force or mass for other planets in the solar system. By 1798, when Henry Cavendish published results from an experiment to measure the density of the Earth, the convenient assumption that only a universal constant was required to complete Newton's gravity formula had become completely ingrained in the astronomy and science community. And so this is how gravity theory transpired. Cavendish's value of the universal gravitational constant was implemented into Newtonian gravity, and this has been essentially unchanged to the present day. In hindsight, we can say this may have been an unfounded assumption, created as simplification and convenience to relieve over 100 years of frustration of not being able to obtain values for the mass of planets via Newtonian gravity, rather than from scientific reasoning or deduction. And so it has been written ever since that gravity has a universal constant. Conventional gravity has been used to accurately propel and slingshot our spacecraft around the solar system. How can gravity theory be wrong? It's vital to know that when spacecraft flight engineers calculate the trajectories of spacecraft, they don't specifically require big G or the masses of any celestial bodies. What they do require is a property of each celestial body known as the standard gravity parameter. The standard gravity parameter is the product of big G and the mass of the planet. Standard gravity parameters can be found by observing the motion of a satellite, such as a moon, as it travels through the gravity field of a much larger body, and by using Kepler's third law of planetary motion. It's worth noting that the standard gravity parameter can be measured more accurately than either big G or the mass of any celestial body. Big G has always been difficult to measure because gravity force is very weak, and the mass of celestial bodies are never measured, they are deduced. So in theory, for spacecraft flight, it wouldn't matter what value of big G is used or what masses we deduce for the planets, so long as the mass of our spacecraft is negligible compared to the mass of the celestial bodies. The standard gravity parameters of all celestial bodies in the solar system are empirically measured and would remain unchanged. The success of spaceflight is not dependent on any given value of big G or any deduced mass of any celestial body. The value for big G given by Cavendish type experiments and the assumption that big G is a universal constant are the main reasons for believing Jupiter is a gas giant. Directly measuring Jupiter's standard gravity parameter, then inputting big G yields the mass of Jupiter at 1.9 times 10 to the 27 kilos, and its density at 1.33 grams per cubic centimetre. 1.33 is too low to be mostly rock. This is how conventional theorists assert Jupiter is mostly hydrogen. In the next video, we'll look at some solar system evidence that suggests big G is not a universal constant.